And with that, we'll go ahead and introduce our first speaker. So Geraint Luff is a DSP engineer from Signalsmith DSP, and his talk is Common Problems with IIR Hilbert Filters.
Yes, I'm audible, great. Although I've called this common problems, and I've made that plural, this talk is just one pet peeve that I have about how Hilbert filters are generally implemented if you just Google how they're done. So a little background, sort of a Hilbert transform, generally, is you've got a signal, and the Hilbert transform rotates the phase of everything in that signal by 90 degrees. The Hilbert filter is, in the way it's commonly used, sometimes called the dome filter when you're dealing with circuits and stuff, even though if you actually Google that, you get plumbing supplies. It takes a real signal and produces a complex signal which is analytic, meaning it only contains positive frequencies. Now, if positive and negative frequencies is a bit scary, then this talk might be confusing, but I'll do my best. So the idea is that you've got your real part being sort of the original, and then your 90-degree phase shift is the imaginary part, and together those produce a complex signal. But actually, that's a terrible way to think about it, and the Hilbert filter, I think, is better considered as a filter that removes negative frequencies and leaves positive ones. So a quick overview of complex signals and negative frequencies. So this is a real signal. And it changes over time, goes up and down. But what's actually happening when it crosses zero? Like, there's only one frequency here. This should be, in some way, the simplest possible waveform. But there's points when it actually is not doing anything. But the signal's still doing something, and at the corners and the top and bottom, it kind of stops. Is it rotating still? And there's nothing wrong with that. You can kind of get your head around it, and there's momentum and all that kind of thing. But in maths terms, the simplest possible thing isn't a sine wave. It's actually a complex sinusoid, which has a constant amplitude, and the phase just rotates over time. And this is simpler in terms of the equations that produce it and various other things. There's more than one of these, so it can be going one direction in the complex plane as you go over time, or it can be going the other. And there's not a hugely intuitive physical representation of what this means. Maybe it's like signals going one way and signals going the other way, and the imaginary bit's related to displacement or pressure or something else like that. But basically, this is the way that we deal with them when we're doing a lot of signal processing. And when we actually want a sine wave, the way that we generally think about it is that it's the sum of a complex exponential going one way and the opposite negative frequency going the other way, such that the imaginary parts of it just kind of cancel out, and you're left with just the real oscillation. So the sine is not the simplest waveform because it in fact has two frequencies in it, the positive and the negative. Okay, so what this looks like when you're talking about the spectrum of a signal is you might be used to just one half of this if you're looking at a sort of frequency analyzer in your DAW. But when you're doing Fourier transforms or similar kind of processing, you have a symmetrical spectrum for a real input, which has positive frequencies, and then every positive frequency has a negative reflection, a mirror of it. And there are some things you might want to do. This is a really common thing to want to do, is frequency shifting, where you, unlike pitch shifting, it's a different talk, you shift everything in the signal by a fixed number of hertz, up or down. And this is actually really easy to do, right? You just modulate your signal with a complex exponential. It's very straightforward. The problem comes is that you need to convert it back to real afterwards. So one problem is you've actually got the mirrored bits are now in kind of the positive region, Maybe that's what you want, maybe it's not. It does mean that like some of the lower frequencies get that kind of ringing, more like a ring mod than the frequency shifter. But the bigger problem is that the stuff that's still in the negative frequencies, when you convert back to real, the symmetry of a real signal and the spectrum kind of reasserts itself. And so the two bits that didn't match anymore now kind of blend together, and it's a bit horrible. So what you really want to do is, this is the Hilbert filter, to take your complex spectrum and then have a version where all the negative frequencies are gone. Because then you can shift this around, you can do whatever you like with it, and then you won't have that mirrored copy screwing things up when you convert back to real and the symmetry reasserts itself. So a particular interest in this talk is what exactly happens around 0 hertz, the DC component. So I did open this by mentioning the Hilbert transform and Hilbert filters. I am going to I'm going to illustrate some stuff, and I want you to not absorb it, if that's all right. So it's very tempting to say, well, what the Hilbert transform is you have your real signal, and you want to make up the imaginary part that turns this into an analytic signal. Or maybe you'll even see a diagram like this, where you've got your real input and 2 filters that are like out of phase. No! Don't do it. It's how you might implement it. I'll go into why I don't think you should do it this way later. But this doesn't really give you many insights into what the errors are that you should expect, how you can reason about the quality of the filter you're implementing. And this perspective is significantly more powerful and helps you make good decisions and analyze and design your own from scratch and reason about whether the Hilbert filter you have is good or bad. Okay, so actually, we work in the digital discrete time domain, so our spectrum is not infinite, it's bounded. Well, if you're going to be really nitpicky, then probably has like infinite repeating copies, but we'll just kind of ignore that for now and say it's a bounded spectrum, and there's some kind of wrapping around that happens at the edges. But the point is that you look at a diagram like this, and you think, well, what I want is a filter with this kind of shape. It passes through all the stuff in the positive half of the spectrum, and it nixes everything in the negative half of the spectrum. Actually, filters don't have those perfectly hard edges in practice. You've got these transition bands where it kind of goes from being 1, or in fact 2, because you're taking away the other. Anyway, it goes from the sort of pass band to the stop band, and there's a bit in the middle where it's attenuating some of the positive stuff that you want, and it's also letting through some of the negative stuff. So generally, stuff where the input is in this transition band range, that's where it goes a bit wrong, and your results can be kind of dodgy. So if you've got a sine wave that's in this transition band, the one you want will come out a bit less strongly, and the negative one will still be there, so you'll still get the same artifacts from the mirrored copy that we were trying to remove. So let's look at a specific example. Let's say, this diagram is not to scale, but let's say we're running at 48 kilohertz. The bandwidth of a filter for a given design and order and everything is generally proportional to the pass band, sort of for something like a band pass like this. So if the pass band here is between 0 and 24 kilohertz, and let's say, pull a number out of thin air, that the transition band is 1% of your pass band. That's a pretty sharp filter, but it means that that region between plus and minus 120 hertz is in the transition band, and inputs in that low range can give you artifacts. Maybe you can high pass your input before you put it into the Hilbert filter to avoid this kind of stuff. Here is the problem. Here is my pet peeve, which is the seed of this talk. Here is the same diagram, but you're running at 96 kilohertz. Same filter, same coefficient, same order, same ripple characteristics, except our bandwidth is now twice as long because we're still passing through half the spectrum. So our bandwidth is now 48 kilohertz wide, our transition band is 480 hertz wide. So that's twice as wide as it was before. Now anything below 240 hertz is prone to these errors. And that sucks. It's sample rate dependent, and a lot of stuff in audio does behave slightly differently at different sample rates, but normally, higher sample rates perform better, and your users will expect that. And you might expect that as well if you've got an oversampling switch in your plugin or whatever, and you turn it on, and suddenly your Hilbert filter just is a bit worse than it was, and that's not good. So, oh yeah, a quick note: if you do go web searching for like how to implement a Hilbert, you'll find some kind of pre-baked coefficients, doom diagram here. Don't absorb it. But yeah, you'll get some all-pass filter kind of recipes for this kind of setup. And actually, these are, as well as not being a very intuitive way to think about it, they're generally very close to being elliptic filters of this form. So when you've got this kind of all-pass setup, what it's almost certainly really doing is an elliptic filter, which have a very nice property that, under certain circumstances, you can separate them into two parallel all-passes. I'm mostly saying this to kind of try and inoculate you against it, because if you see this kind of dual all-pass setup, no, it's doing a half-band filter, and it's subject to this problem where it gets worse at higher sample rates. So, what can we do? Well, one solution is to use better filters as the sample rate goes up. That would work, and I don't know, depending how you scale your order with your input sample rates, maybe it gets better in the way that people kind of expect. The downside is you need to be able to, you probably want elliptic filters because they've got that really good, sharp cutoff compromise between like order and CPU and various other properties. But they're complicated to design. Like, I've bashed my way through the maths of it, and I still don't have like that intuition of like where it comes from in a way that would let me explain it to anyone else in a way that I'm happy with. So you do have to be able to design elliptic filters, and not just any elliptic filters, but weird ones that aren't centered on zero. And also, if you change the order and other characteristics, the ripple and so on, then your phase response changes. Maybe this is no issue, but I have seen people who are using the Hilbert filter inside feedback delays and that kind of thing, inside phaser-like structures, and there the phase response ends up being part of the sound. And so when that shifts around, you're actually in trouble. So yeah, another approach you can do is to get mathsy. This is a pretty nice paper that just kind of goes over a very clean way to design Hilbert filters, and like the main thing that it does, or I'll zoom out, nope, not all the way, is this is your, I put ripples in because that's how elliptic filters tend to work, and using very similar maths to the thing that makes your EQs get all funny and scrunched up in the high frequencies, it pinches the low frequencies together to keep that transition around zero nice and sharp. This is very cool. It's good to see that used for good instead of evil. Pros and cons. It's pretty cool. Con, it's pretty tricky. You've got to do some maths, and if you're not someone who can make their way through an academic paper, then that sucks a bit. And again, you still need all the toolkit in code, imported if you didn't write it and need to find a good one, or writing your own if you're in an environment where you can't do that. And you need to do pole zero manipulation and various other things as part of this. So like, you know, MATLAB already does that stuff, and that's great, but the moment you're on your own with just like C on an embedded platform, then this gets a bit more demanding. The approach that I would recommend is, instead of saying I'm going to pass through all the positive frequencies and get rid of all the negative ones. You instead have a fixed bandwidth for your Hilbert filter, because this is audio. We can get away with this. We only care between 0 and, say, 20 kilohertz. This means that the passband region for our Hilbert filter, our complex filter, is always constant. So our transition band, which is the bad bit near 0, is also constant, regardless of sample rate. So yeah, pros of that, consistent transition width, and the phase response is also, it varies a little bit because of bilinear what's-its, but like, it's much more consistent than the other approaches. You probably still want elliptic filters when you're doing this, but honestly, it's not a deal breaker. Because, yeah, the thing is you actually only need simple elliptic filters. I will show you why. That like, although, I've done it again. Yeah, you don't need really full complex toolkits for elliptic filters. You can use much more simple off-the-shelf things. So we're going to make our own Hilbert filter out of parts you have at home. Maybe it's biquads and the Audio EQ cookbook. Maybe it's juice. But you start with this real signal, which has a spectrum like this. It's all symmetrical and reflected and conjugate. You down modulate it by 10 kilohertz. This is done by just multiplying it against a complex exponential that's oscillating at minus 10 kilohertz. Then you do what looks pretty much like a conventional low pass, and I'll get to that in a bit, to just get the stuff between plus and minus 10 kilohertz, and then you upshift that result. And voila, you have essentially kept all the stuff between 0 and 20 kilohertz and removed everything else. Now, the wrinkle in that is that I have not really, I've just said, yes, apply a filter. If this was a real signal, this would be off the shelf. For a complex signal, it's almost as simple, because all you need to do is have 2 low passes. You apply 1 low pass to the real part, 1 low pass to the imaginary part. I'm saying this because most DSP toolkits only have filters for real valued inputs and not complex valued ones. That being the whole problem that sort of we're trying to get around here. But the point is, you can make this out of very simple parts that you have in your own kitchen and a yogurt pot. So here is some C++ code, which I have not in any way tested, and I wrote it on the train here. So, but the point is, you have 2 low-pass filters for your real and imaginary parts, and you have a phase step, which is going to be running at, it makes our phase go round 1 cycle every 10 kilohertz. And then for every input sample, which is real, increment the phase, avoid numerical accuracy issues, turn that into a complex exponential. We down modulate our input by multiplying it with the complex exponential. The conjugate function here, it flips the imaginary bit. It turns a positive 1 into a negative 1. So it's, that's turning our complex sinusoid into the negative frequency. So we down modulate it. We apply 1 low pass to the real part, 1 low pass to the imaginary part, and then we up modulate it. And we're done. That's it. So I will say, off the shelf, like a biquad low pass is not going to cut it. The cutoff is nowhere near sharp enough. Because remember, typically the cutoff for a biquad, for a low pass kind of thing, is it ends up at whatever it is, 10 kilohertz. So it doesn't matter if it's 100 hertz wide, or a kilohertz wide, in fact. But this is, whatever that width is, it's going to be happening near 0. So generally, biquads are not going to cut it. You do want something elliptic if you can do that, if you have it to hand. So if you're using juice or whatever, those have that in the toolkit. If you don't, and all you have is biquads, you can make high-order Butterworth low passes by stacking together other second-order low passes with just different Q values. Here is an excellent page on ear-level engineering that gives a little illustration of how it works, and also a little web tool which tells you what Q values to use. So you just stack, I don't know, 20 low passes in a row with different Q factors, and then the end result of that is a Butterworth with a really nice phase response and a pretty sharp edge. I also threw something together and just thought I might as well kind of show you what the performance you can get out of this is. So this I've just done by, I've designed a filter in Python and then kind of pulled and pushed and stretched it. But yes, this is a 16th order filter, and you can see this is the 48 kilohertz response, and that it's passing through stuff between 0 and 20 kilohertz. This is my impulse response at the top, and this is my decibels. And between 0 and 20 kilohertz, I've told it to have 0.5 dB of ripple, and then below 200 hertz, it's pretty negligible. And then you can see the same filter class running at 96K, which now you can see in this actual real working example plotted from C++ code, what it is doing for a higher sample rate. It's keeping less of the spectrum, but that transition at the bottom is still the same width, because we're not making our band, our pass band wider. And that's the talk. Given that I'd not practiced this, I have no idea how long that took. I hope it was interesting or useful for anyone who either already has a Hilbert filter and doesn't know whether it's good or not, or maybe wants the confidence to kind of mess around with it and try it yourself. You can build one of these yourself using off-the-shelf components that are just available in any sensible DSP toolkit. Yeah, I'm Geraint Luff. If you have any questions or any other crunchy problems that you want to ask me that I might be able to help with, then yeah, give me a shout.
Okay, we have a couple minutes for questions. Please raise your hand and I'll come over to you.
So years and years ago, ran into, there was an algorithm for a frequency shifter that was basically trying to do similar things, not so much for Hilbert transforms, but to emulate some of the analog frequency shifters in modular synths and that kind of thing. And they did a similar trick, but instead of shifting down, they shifted up, and basically used a polyphase filter to downsample to basically bring it back into the audible spectrum. It was a similar sort of thing of the rotations, but then wanting to get rid of the mirrored signal, so it actually sounds like a frequency shifter rather than a ring mod. And I just wondered if you'd been inspired by any of that stuff. I think it was a Laurent de Soras from Ohmforce's paper, but I could be wrong on that.
Yeah, I don't know which specific thing you're talking about, but there are lots of ways to cook an egg, basically. So whether you upshift and then up-pass and then kind of digitally alias back down to the audible range, or you downshift or whatever. Even a lot of the analog circuit designs that I've seen, some of them do, they have a modulator that splits one signal into two, which are essentially the real and imaginary parts, and then you low pass it. And that's sort of a common-ish design. I don't know about the high pass one, but like, yeah, if you send me a link afterwards, I'll read it, yeah.
Okay, with that, one more thanks to Geraint Luff.